Okay, and so there are several different possible variations of the folded flexure design. So this comes from Mike Judy's thesis. Mike Judy is a fellow at Analog Devices now. So these all basically use the same kind of suspension, but they're implemented in different ways depending on how we want the structure to move. So one you can see here is just two anchors in the middle. This is sort of like the analysis that we started out with. There can be another situation where we have the two anchors on the outside here, so we have a total of 4 anchors. Or we can have cases where we may have a discontinuous truss. These ones where the truss is broken aren't quite as good because there can be twisting rotations. So like if you imagine this kind of twisting, then that will basically cause this thing to translate and this one to translate the other direction. With the continuous truss, this center beam here sort of acts to resist that. So whereas this one, where we've cut that, we make it less resistant to that. So this one, or this one here, or this one here, we can have problems with twisting vibration modes that these other ones won't have. Similarly, if we have like we have any sort of things that acts to kind of bend this part of the truss, when we break this thing, we resist the ability to, that we reduce the stiffness in response to those kinds of loads. There are other designs, for example, where we might have the anchors to one side in the moving structure over here, or perhaps we break the anchors in two and have the flexures like this. So these are all different possibilities, and depending on how you find that you have to put your actuators, then all of these may be things you might want to consider. Now, if we look now at the details of the deflection of this thing, here's the anchor, here's the moving proof mass or shuttle, and this is what I want you to do is imagine that this is symmetric. So the other side of the suspension is on the opposite of this symmetry line. Right, so looking back at these designs here, basically what we've done is we've drawn a line of symmetry in the middle, and we're considering only the top suspension. And the way that this is drawn here, we can see there's a force here, F, pushing on the suspension, and 1/4 of the force is here, the other quarter of the force is on this beam, and the other 2 quarters will be on the symmetric side on the other side of the structure. In terms of the thinking about the releasing of the axial tension, well, if you look at the way this structure deforms as the proof mass moves, we see we get this sort of a bending shape, right? It looks like the fixed guided beam here, and it's fixed guided here. And so the change in the length along here, let's just call this delta y for now, right? So each of these beams has the same deformed shape, and so they want to have the same delta y, and so the truss can basically take up that change in length, so there's no axial tension in this beam, and that makes the suspension very linear. Now, in terms of what we talked about before, you can see that there's 2 beams in parallel, 2 fixed guided beams in parallel, and then over here there's 2 fixed guided beams, and hopefully I can convince you that these 2 are in series with these 2, and so the 2 that are in parallel, well, their spring constants add here, but then these ones are in parallel, and so we get that the net effect is that the spring constant of this half of the suspension, we have 1 over k, is going to be equal to 1 over 2 fixed guided from this part here plus 1 over 2 fixed guided from these 2 guys, right? So I've taken the compliances add for the 2 that are in series, and so what we get is that so the spring constant for this whole thing is just the spring constant of the fixed guided beam. Okay. So this is sort of a summary of this thing. You can analyze it by looking at the bending of any of the individual beams, but what you'll find is that the spring constant of the whole folded flexure, K, is equal to the fixed guided spring constant, and I wrote that back here in the box here. Okay, and this turns out to be equal to 4 times the stiffness of a cantilever with the same length. Okay. So in this analysis where I looked at the parallel beams and the series beams, really we're talking about the stiffness of this part of the suspension. It's only half of it, so the total spring constant is twice this amount. Here, I will use it on a different page. So this counts both sides. Okay, that's all that I have for this time. So in the next lecture, I'm going to start to talk about energy methods and how we use that to analyze the bending of beams, including nonlinear effects from axial tension. But that will wait till next time.